after that performance of our software downstairs, I'd say we've pretty much nailed Poisson's equation pretty well. So now we're going to move on to the rest of density functional theory. And as we've been emphasizing, that basically boils down now to, we've got the rest of it all figured out. What's left just boils down to carrying out some sort of a minimization. And we might want, particularly for bigger problems than the quantum dot one on the next assignment, we're going to want more powerful minimization methods. So that's basically what this component of this lecture is about, is, well, how do we really go beyond steepest descents? And as I had mentioned, when I first introduced steepest descents, I think a general feature of all numerical methods is that, in the end, the most advanced methods really just seem to be tweaks on very simple ideas. And that's what we're going to see today, right? We're going to basically look at this steepest descent algorithm, and we're going to tweak it up. And we'll end up with one of the most powerful nonlinear optimization methods that's available today. And it's all going to come out by doing an analytic analysis of the performance of the simple idea. And I found time and time again you can understand all the more powerful numerical methods from that kind of a perspective. And then there's just a little bit of an art to, well, how do we analyze the performance of a numerical algorithm like this? Now, to analyze its performance, usually, so this is what I'm saying, right? To improve, what we like to do is we analyze, or do an analysis of the simplest algorithm. And then for the analysis, it turns out, in very many cases, particularly dealing with continuous equations like we often come across, the analysis at some point or another is always going to end up being based on some Taylor series expansion. It's a constant theme over and over. And there's a very good reason for that. And that reason really comes to the fore in electronic structure calculation. Just kind of as I was showing you downstairs, we often like to carry out calculations to fairly high precision. In the electronic structure context, for instance, you know the basic energy scale is the Hartree, right? So our total energies are going to come out to be, a few, 10, depending on how many atoms, 100 Hartree. A Hartree is 27 electron volts. The accuracy of density functional theory is about 0.1 electron volts. And numerically, you always want to carry out your numerical solution at least an order of magnitude, or maybe two, more accurate than you expect your theory is. For the simple reason that you want to understand the errors in your theory and not the errors necessarily in your numerical solution. So that means, when you run all the numbers, something good to keep in your head, by the way, is that if you ever have to deal with Hartrees, right, is that 1 milli-Hartree is very close to room temperature. In fact, in some places on Earth, it is room temperature. Right? What was your example, Shankar? You've been somewhere where it was a milli-Hartree, right?
Yeah.
Where was that?
In India, it reaches the milli-Hartree all the time.
All the time, right. Baghdad, milli-Hartree, maybe Alabama, I don't know. Not so much New York State, but you come pretty close. It's close enough for physics to call it room temperature. Room temperature is a few hundredths of an electron volt. We'd like to be a little bit better than that. So we want sub-milli-Hartree numerics out of a calculation that's going to have 10 Hartree in it. So we're going to need a precision of 10 to the minus 4 or 10 to the minus 5 in our solution. Something like that. When you need that kind of precision, it turns out that as you, say, do a minimization algorithm like this, you're going to spend almost all of your time in this kind of iterative search, quite close actually to the minimum. Right? You're just sitting there refining, cranking out those last 4 or 5 digits. Most of the time, you're near the minimum, where the function looks quite much like a simple quadratic form. And it's because of this kind of high precision numeric aspect of a lot of physics problems, because you're looking at subtle differences between systems that have some large total energy associated with them, that a Taylor series expansion for the behavior of your functions usually turns out to be a reasonable thing to do. So that's how we're going to approach this. So my approach then is going to be say that whatever this function f of x is that I'm minimizing, sort of in my canonical statement of my minimization algorithm, I'm going to expand it. And where should I expand it around? Well, clearly I have to pick some point, and the solution point is probably the best point. After all, that's the point I'm hoping I'm going to spend most of my time close to. So we'll expand around the actual minimum point, which I will call x star. This is the actual minimum. And then, you know how to do its other series expansion, x minus x star, dot with the gradient of f at x star. And this quantity here, by the way, I'm going to call delta, which is really just the error in my solution at any particular stage in the solution, right? How far away I am. Now, when you do these Taylor series expansion analyses, there's the next question always is, okay, what point should I expand around? Then, to what order shall I expand? Well, generally speaking, the answer is going to be to the first non-trivial order. Now, this order, the first order, is clearly trivial because the gradient of f at x star, since x star is the solution, the gradient there is going to be 0 because I'm at a minimum. So I'm going to clearly need some more information about the behavior of my function. Then the next term, typical quadratic term, is 1/2 my displacement from the solution. Right? Well, it's a quadratic form, so I like to do it in vector notation again, my column vector thing. So this should be transposed or daggered. It's all real numbers now in this analysis, either way you want to go, through the Hessian matrix times the error vector again. And I'm going to hope, and we'll see as the analysis carries through, that indeed this is the first non-trivial order. And I'll tell you exactly what I mean by that in a moment. Where B here is just a matrix. Let's see here, I just want to remember how I was going to do all my notations. Alpha, beta. It's just the matrix of mixed partial derivatives of my function at the solution point with respect to all of the relevant coordinates. It's the Hessian. I call it B for reasons that I'll also make clear a little bit later on in the lecture. And it's always nice. Now, how should I put this? We don't know what B is, right? We're never going to know what B is because we're never going to actually get down to the bottom solution. It just suffices for us in this analysis, as you'll see, to know that B exists and it's going to have certain properties. And some of the generic properties are always good to think about. Well, as you know, mixed partial derivatives are equal, right? So B is going to be symmetric, or in my lazy physicist language, Hermitian. B is going to be Hermitian, symmetric, whatever. And what else do we know about this matrix B? Yes? Oh no, he's just crazy. Well, we're looking for a minimum, so what does that tell us about the Hessian matrix? It's, yes, positive definitely. Which will become very important later. Okay, right? Right, that's the thing. Like these numerical physics things, these numerical algorithm things often turn out to be like, third semester calculus type things, right? So it's got to be positive definite because I'm looking for a minimum. So that's my model for my function. And now the game I'm going to play is I'm basically going to take this model, put it into my algorithm, and see how it behaves. Now, we need one more piece of information to do that. Much like when we did the numerical work, we had the total energy expression, which is like having f. The final piece we needed, of course, was the gradient to see how the algorithm would work. So we're going to need the gradient of my function f of x within this model. And that also is fairly straightforward, right? This guy here is a constant. That's the minimum value. So that gives me 0. This thing here already is 0. And I just have to take the derivative of this symmetric, positive, definite quadratic form. And you guys know how that goes. The derivative with respect to x, then you'll get two different contributions from each of these two x's, but because this is symmetric, they're the same, which kills the factor of 2. And you just get your matrix back times your error, your distance from the solution. x minus x star, or if you want, that's just b times the error vector delta. So now we're ready to carry out the analysis. So how does this work? So at the beginning, we're going to make some initial guess, x naught, which then will imply some initial value of the error that you're starting out with, x minus x star. And by the way, just a little note, in general, I'm going to say that I'm going just to define the error I'm making at any particular step in my iteration as naturally enough the difference between where I am at that iteration and the final solution. So that's the first part of my algorithm. It just defines my initial error. Now here's where things get a little more enlightening on the iteration part. So in the iteration, I have xn plus 1 equals xn minus something. So xn plus 1 from this definition is just my solution point plus whatever the error is at iteration n plus 1. Right? And then that's going to equal xn is my solution point plus my error at step n. Right? So that's xn. This is xn plus 1 minus alpha times the gradient of f at point xn, which would be b times xn minus x star, or just b times delta n. Just directly substitute. Now, something very nice just happened here, right? You'll notice that my x stars have canceled out, which is nice because we don't know what x star is going to be, and I have to carry out this analysis. It's also nice because it tells us that, for instance, the error at the next iteration is going to be proportional to the error at the preceding iteration, without any zero-order terms entering in. If some zero-order terms entered in, that would mean I messed up my algorithm in some royally bad way. Okay, so those cancel. The other nice thing, which I pointed out, is that it turns out that the value of delta at the next iteration is just some linear operator acting on the error on the preceding iteration. I could write it as this operator, 1 minus alpha times the Freudian matrix times the previous iteration. So the iteration just applies a certain operator to the error at each step. And that also makes it easy to write down the error on the nth step, because that's just going to be n applications of the corresponding operator. Right? That was easy. Good. So we're going to expect then that these kinds of algorithms are going to, evidently, they give us some kind of exponential convergence. So even good old sequence descent isn't that crazy. Right. Now, to try to and the other thing I wanted to point out to you is notice that with this particular algorithm, the error at the next step doesn't seem to be 0 at this order, right? It's still going to be non-zero. If it were 0 at this order, what would I have to do in my analysis? Right? I would have to have carried out this expansion to the next higher order. Right? That would have taught me that this algorithm is powerful enough to reduce the order of the error at each stage. This particular one is not. We will see one coming up that actually gets close to that. And that's what I mean by first non-trivial order. It's actually the first order that your algorithm doesn't get right on each iteration. Now, to make further progress, we can now use the properties of the matrix B. We don't know what it is, but we know it has this nice symmetric and positive definite property. That means that we can look at the eigen values and vectors of B, which I will call eigenvalues Bn. No. use n for iteration. bi, I'll call it, and e hat I for the corresponding eigenvectors. And notice, because b is positive definite, I know at least that all the bi's are greater than 0, which will be. Okay, well, what can I do now that I have this eigenbasis and these eigenvectors? Again, I don't know what they are, I just know that they're out there somewhere and there's something. Well, again, looking at each step of my iteration, this means, for instance, that the error on step 0, I can clearly expand in my eigenbasis as some series of errors along each of the different eigendirections, with a certain magnitude error in each case. And then the error on the nth iteration, evidently, I just have to apply 1 minus alpha b to the nth power on delta 0. I'm not going to, I guess I will write it out. Delta I, e hat I. Ah, that is one pokey son of a... Well, while we lock this, maybe you guys can think of what that expression is going to turn into. Do you have the key for this one?
You have it.
I have it. I don't have it on me.
It'll survive.
It'll survive. Okay. Well, it's a linear operator, so clearly I can pull the sum out and these constants out. And then each time I apply this operator to an eigenvector, because it's an eigenvector of b, I'm just going to get something times ei back again. So I'll get ei back again. And that something will be the same as I do this n times in a row. Right? So it's going to be to the nth power. And what that something is just some scalar times ei. And it should be then, I'll get ei minus alpha b on ei is just little bi on ei. Right? The eigenvector. So this is 1 minus alpha bi to the nth power. So now, evidently, right, I'm going to have exponential convergence. And the convergence is going to depend upon which direction in the space I'm in, right? And different directions will have different amounts of convergence. Some will have more, some will have less. Ultimately, the performance of my algorithm is going to be determined by the slowest to converge mode. Whatever one has the slowest to converge factor here is going to be the one that's going to dominate as the solution proceeds on. Now let's think about what these numbers are going to look like. As I said, bi is always positive, right? So I want to get something less than 1 here. So, sometimes I'll get numbers like 0.5, right? Well, that would just mean this thing can, the error reduces by a factor of 2 each iteration. Nice exponential convergence. I might get numbers, this would kind of be not so good, but if b is very small, some of these guys might be like 0.999. Those are going to take a little longer for me to converge. Right? So from this point of view, you'll notice that the convergence is dominated, right, as I said, by the slowest to converge factor, which will be 1 minus alpha times the minimum value of b. Right? The little teeny one here is going to be the one that gives me something closest to 1. So I want alpha then to be as big as possible so that when I do 1 minus alpha b min, right, I'm not hanging around 0.999, and I do well in my algorithm. So that gives one feature that you want alpha as big as possible. And by the way, this is something that you're going to face in the assignment coming up. In the assignment coming up, we're doing a steepest descent solution, right? And alpha is under your control, and you're going to find, well, if I make alpha small, it's going to take a long time to find the solution. That isn't too shocking if you think about the Ithaca algorithm, right? It's just saying, well, if I'm taking teeny-weeny steps downhill, it's going to take me friggin' forever to get to the bottom of the hill, right? So I want alpha to be as big as possible, but there are limits. you can make alpha too big. And what will happen when alpha is too big? Someone tell me where the downside to a big alpha might come in. Yes, I see someone going like this, right? If alpha gets bigger and bigger, you go from 0.999 to 0.5, eventually 0.1, that would be good. If you go too far, this could turn out to be like minus 0.3. Well, that's okay, right? It'll still converge down to 0. But some might be minus 0.8. And then when you get to minus 1.1 or so, now you've got a problem, right? It's just going to diverge exponentially. So you'll have to watch out for that on the assignment too, right? Too large, alpha. There are two signatures to it. One is you diverge exponentially. And you find oscillatory solutions. And this, of course, begs the question, well, what's the limit? Right? The limit is that 1 minus alpha. And, of course, it's the biggest b that you're worried about. Because the biggest b is going to be the first one where alpha is going to push you past minus 1. So 1 minus alpha times b max had better be greater than minus 1. Right? It can't be more negative than minus 1. So you can solve this and you'll find that alpha then has to be less than, right? Because you put this one over here and you get a 2. And the alpha's on this side, so there's no minus signs to mess you up. So you don't have to flip that 2 over b max. So that's the absolute limit on alpha. Can't be that much bigger. So then the final convergence rate is controlled by the factor 1 minus this best alpha, which was 2 over b max. And over there it's times b min to the nth power. And this thing has a special name, b max over b min. Does anyone know what that's called? Numerical work? Some people might know. That's the condition number. Very good. Condition number. It's basically the range in the spectrum in the Hessian. We call that C. And so the best you're going to do is 1 minus 2 over C to the nth power. And the condition number, unfortunately, can be, thousands. And so if you've got 1 minus 1/1000th, which is 0.999, this guy you have to raise to the 1000th power before you get to 1 over e, right? So you have to do 1,000 iterations to get an improvement of factor 2 or 3 or so. If you want 16 digits, you're going to be around for 50,000 iterations or something. That's not going to be too good. You'll get there, as long as you don't make alpha too big. It just might take longer than you want. Okay. So that's how steepest descent performs. So let's try to figure out what we could do better. When we think about what just limited the convergence here, you notice you're caught between, as they say, you have a bit of a dilemma, right? You want alpha big so that you can converge quickly, but a big alpha might help some of your error directions, or error modes, I like to call them, but it might be bad for other ones. What might you do to alpha to improve upon that kind of situation?
Different alphas for the different ones have an alpha vector which...
Right. That's nice. He would like, rather than to have one alpha for all of the directions, right? He would like to have a different alpha for the different directions. So one idea is different alpha for the different e hat n's, right? Now, if you think about that, what he's really saying is alpha can't be a scalar, right? It has to have a different action on the different eigenvalues. Well, that just means, basically, alpha a matrix. Step, a linear operator. Now, if you look at the algebra here, the way I wrote it, I always wrote alpha before the gradient of f. And I never commuted these two. So alpha actually could have been a matrix throughout my whole derivation. I was careful about that, right? So, you go, well, we missed this part here, right? But then, here's the basic iteration step. This could have been a matrix. So you would have matrix alpha times b, right? And you would have come precisely to this conclusion here, right? So that actually tells you what alpha you would want. Alpha, a matrix. The best alpha would be what matrix?
Inverse of B.
The inverse of B. If alpha were the inverse of B, then this would have given me 0, right? And I would have a higher order algorithm, a quadratically convergent algorithm. And that is the basis of things like quasi-Newton methods, basically. That's what they do. Now, these things get a little tricky. We're not going to go that route. Because, well, our vector space, as you saw, we had a grid. What did we finally end up using? I think 40 cubed, right? So that would be 4 cubed. That would be 64,000 would be the size of my vectors. That's how many degrees of freedom. Well, that matrix then would be 64,000 by 64,000. So you can see pretty quickly you don't want to store that thing. Okay, what's 64,000 squared? Well, 1,000 squared is a million. 64 is 2 to the 6th, 2 to the 12th, right? 4,000, right? No, 4 million, right? Did I lose track? Yeah. 4 billion, right? Wait. What was it? 64,000, I got myself all messed up, right? So 1,000 times 1,000 is 10 to the 6th, and 64 squared we just worked out was 4096, right? Yeah, so 4 gigawords. And each complex number is 16 bytes, so that's 64 gigabytes. All right, we're not going to do that. Okay? There are methods where you don't actually have to make a copy of the matrix and then invert it. Those are known, one of these, which is one of these quasi-Newton's methods, known as Broyden's method. And that actually is just why I mentioned the matrix. So we're not going to be able to do that. But we can do something. What we can do is, we're going to let alpha basically be a matrix, which I'll call K. And K is going to be some approximation to the inverse of B. And when you do something like this, it's known as a precondition. And I'll show you a little bit more how that works later on. But the idea is that you can do maybe you take the diagonal elements of B as a matrix and invert that matrix. Right? That's a much smaller, it's diagonal, it's much less data. You can do something like that. And alpha does not have to actually be the inverse of B. It just has to make the condition number of alpha times B a lot smaller. And then you'd be happy. Right? Good. So that, then, is the first generalization on these minimization algorithms. And this thing would be known as preconditioned, or I would call it, well, certainly everyone calls it preconditioned. I would call it preconditioned steepest descents. And the algorithm looks like this, right? Have some initial guess. You compute now a search direction, which isn't necessarily your gradient, but it's minus this preconditioned gradient multiplied by k, your gradient at that point. And then you step along that direction. Since k is not going to be exactly the inverse of b, particularly because we're approximated somehow, it's still prudent to take some, maybe smaller step size downhill. So you can still have an alpha if you want in your algorithm. If you don't mind my mixing senses a little on you, right? Some step amount down that search direction. And iterate there. Good. So that's one way to get a different alpha for each search direction. There's another way, and we can combine it with this. It's hard, to have analytically different alphas for different search directions, right? Because there's a lot of them. I have to make some big matrix or something. But we can at least focus on finding the best alpha for the search direction that we have. Right? So when I'm making this step here, there's just one search direction that I'm interested in. Maybe I can find a way for, at least along this one direction dn, finding the best possible alpha for that direction. And that's a process, well here, I'll indicate it in here. Just as another tweak, you have an extra step where you find best by some criterion, we'll have to specify, best alpha, which I'll call alpha star sub n, for direction dn, right? And then you would use not just one alpha for all of these, but the best one each time you're taking a particular step, like that. And that would then have a slightly different name. So can anyone suggest a criterion? I'll draw a picture of what it is we're doing. Right. Basically what's happening is here's a picture of my space of all possible x's, right? And here I am at point xn, and I've done some work and tried to figure out the best possible search direction, dn, to travel along, right? And then the question is, how far should I go out along this line, right, to find the right amount, alpha n, to find what's best for that particular search direction. What could define the best possible choice there, do you think? What do you think would make a good choice? Yes?
If it's changing rapidly, you probably want a short direction, a short distance.
Very good. If the function has, it depends upon the behavior of the function, right, along this direction. So let's think about that behavior. So if I make a plot of the function f at xn plus alpha times dn, right, as a function of alpha, let's see how this guy is going to behave, right? Well, when alpha is 0, that's just f at xn. Okay. Now, a little technicality for you guys here, but it's usually best if k, we like k to have two properties. We like it to be a symmetric matrix. That shouldn't be so bad since it's supposed to be a model of the inverse of a symmetric matrix. Right? We also like it to be positive definite. These are more technicalities for you. And that's also should be not unreasonable of a restriction since B is a positive definite matrix and so therefore should be its inverse. If that's the case, it turns out that you can prove, I'm not going to bother right now, that as you move along alpha, the derivative of the function at xn should always be negative. You're going downhill, basically. Right? If it were this, you'd all definitely agree it should be going downhill. But if you make sure k is positive definite, you can assure yourself it will be. So the function starts going like this, right? And now he suggested that if the function is changing too quickly, you don't want to go so far. Well, let's see, what is this function going to do? Well, it's going down, right? It can't go down forever. Eventually, it's going to come back up because this function has a minimum. So it might be, for instance, that the function has a, is rapidly changing, as was suggested. In which case, then, you wouldn't want to pick an alpha out here, now, would you? What alpha would you want to pick?
Something proportional to inverse of eigenvalue in that direction.
True, but to accomplish what? Which point? In this example, what alpha should I pick? The minimum, right? We want to pick this one. And he just suggested actually a way we would compute that. My point, though, is that there are a lot of good methods out there for minimizing a function of just one variable. Right? You can do something. There's all kinds of stuff. You can do like a grid search. You could do, better than that. There's all kinds of algorithms. We'll learn some simple ones. And remember, we're always near a quadratic minimum anyway. We spend most of our time there. So if you know this thing's a parabola, you can pretty much find the minimum pretty quickly. The point, though, is that you want the alpha, which will minimize your function along your search direction, is the best possible choice for that direction. So this step of the algorithm is called line minimization. So when you put that extra step in, what you're doing is preconditioned line minimization, which is pretty powerful. But you can do just one little bit better than that. And you'll have a chance to compare all of these on the next assignment. So the most powerful one in this class is preconditioned, because you like that preconditioning, something known as conjugate gradients. And again, it's just a variation on this theme here. So it looks very much like our current best algorithm. You have some initial position. They all start out that way. And then you compute a search direction. But then there's a little extra tweak on this. That's what makes it conjugate gradients. I'll come back to the tweak in just a second. Once you have your search direction, you do a line minimization, a lin min, to get the best alpha star for that particular iteration. You then move that distance along your search direction. And the tweak is the following. All you have to do is mix in just a little bit of your previous search direction. So you have to put in just a little bit of the preceding search direction to turn this thing into conjugate gradients. How much? That takes us into a longer discussion, which unfortunately will be beyond the scope of this course. Usually when I teach this unit, like in the computational physics course, it's like a 35-minute little lecture to prove a bunch of stuff. In the end, though, it's chosen to make the gradients conjugate, which, wait, no, it's going to make the gradients conjugate or the search directions? The gradients. Which means that if I make this choice, I will guarantee that the gradients at different iterations, right, when measured through the preconditioner, which is a positive definite symmetric matrix, so it's just some measure on your space, right, will be orthogonal through that measure. Well, proportional to Kronecker delta n. Yeah. What that means, basically, we don't have time to go through it all, is that once you've done a minimization along a given direction in the space, you're done with that direction. There's no need to go back and revisit it. So you quickly basically build up an exact model of the inverse of B in the subspace that you visited. And by the time you've gone through n dimensions, if n is the size of your problem, you've gone through n iterations, you have a complete model of that matrix B implicitly in this algorithm. And you will be sitting at the exact solution. Short of that, it just converges much more quickly because once you're done with the direction, you don't mess it up on subsequent iterations. Now, yeah, it's a bit of algebra to prove that this thing will be a proportional to a Kronecker delta if you make the following choice here. But you guys will just have to take my word for it. There's actually a variety of choices for this that are all equivalent if you had a perfect quadratic form, but are slightly different depending if you've got nonlinear pieces in your function. But the simplest, I think this is the Fletcher-Reeves form, is where you measure it looks like this, by the way. You can kind of guess that somehow this guarantee is built on this structure. You measure your current gradient through your preconditioner and normalized by the preceding gradient from the preceding iteration measured through your preconditioner. And if you do that, if it were a perfect quadratic form, you would have this condition and you'd solve exactly in n steps. And all of these different formulas for this combination, what's here? Polak-Riviere, there's a whole bunch of them, I can't remember them all. They're all equal to each other by an identity if you're in a perfect quadratic form. But real life is not a perfect quadratic form. And you know how these things are when there's really no real reason to prefer one over the other, but there are names attached to things? There's a lot of sort of, well, if you go into this is my favorite trick. If you go into a numerical analyst bar and say Fletcher-Reeves beats Polak-Riviere, then you can step back and watch the action. They'll go at each other. But in my experience, there's really no reason to prefer one over the other than certain names are attached. People like them. So, anyway, that's the algorithm we'll finally use. And like I said, there's a bunch of algebraic manipulation and proofs. It's like 35 minutes. In other courses, I'd be happy to take you through, but I think this is good enough for now. Right? So this is what we'll implement. And very good. So next class will be on Friday. We'll be back in here, and the next assignment's out, and you can start doing some quantum dots on it.